we covered two fundamental properties in machine learning: regression and dimensionality reduction. In this set of videos, we'll have a look at a third pillar of machine learning, density estimation. This set of videos deals with the Gaussian mixture model. To apply machine learning to data, we often aim to represent the data in some way. In density estimation, we represent the data compactly using a density from a parametric family. For example, we may be looking for the mean and variance of a dataset in order to represent the family compactly using a Gaussian distribution. The mean and variance can be found using tools like maximum likelihood or maximum a posteriori estimation. We can then use the mean and variance of this Gaussian to represent the distribution underlying the data. In practice, however, Gaussian distributions and other distributions have fairly limited modeling capacity, so we look for a more expressive family of distributions, which we can use for density estimation. These are called mixture models. Mixture models can be used to describe a distribution P of x by a convex combination of k simple distributions. This is of the form P of x equals the sum of pi k pk of x. With components pk are members of a family of a basic distribution, like a Gaussian or Bernoulli, and the pi k's are the mixture weights. Of course, these pi k's then have to be between 0 and 1, and the sum of the pi k's must equal 1. Mixture models are more expressive than the corresponding base distributions because they allow for multimodal data representations. That is, they can describe data sets with multiple clusters. Gaussian mixture model is a density model where we combine a finite number of k Gaussian distributions, n of x given mu and sigma, so that the probability of x given theta is equal to the sum of pi k n of x given mu and sigma, where the pi's range between 0 and 1, the sum of the pi's is equal to 1, and theta is a set of parameters mu, sigma, and pi for the model. This convex combination of Gaussian distributions gives us significantly more flexibility for modeling complex densities than a simple Gaussian distribution would. Here's a very simple example done entirely in picture form. What we have here is a weighted mixture density made up of three mixtures. The first one is n of x given -2.5. So if you look at the diagram, we're looking at the blue dotted line. That's a normal distribution with mean -2 and standard deviation 0.5. Variance 0.5. Second piece, component 2, is the orange dotted line. That's a normal distribution with mean 1 and variance 2. Third dotted line, the green dotted line, component 3, is a normal distribution with mean 4 and variance 1. Now when we add 0.5 of the first one, 0.2 of the second one, and 0.3 of the third one, we end up with the black GMM density function. So if we have data that has this sort of a shape, we're able to easily model this using 3 Gaussians rather than 1. In the next video, we'll show you how to actually put these Gaussians together.